We're going to pick up in the second part of 4.3 that we talked about. So we kind of started more of the graphing stuff in part one. So now we're going to look at part two here, which kind of breaks into some of the natural log and the common log items. So here at the top of the screen, we have what's considered a common log. And a common log is anything with a log base 10. So we actually don't write the 10 as the base, we just write it log. And these two, common log and natural log, are what your calculators use as default. So if you do not see a 10 here, it's automatically a 10. Down here with a natural logarithm, instead of writing log base e, which is that natural number we've talked about, we can just write ln. And again, that is on your calculator, log and ln by the 7 and 4 button on most calculators. And then the properties of natural logarithms are the same properties as our other logarithms before, except they just put it in terms of ln. Okay, so here with your ln1, this is like saying e to the 0 power is 1. Anything to the 0 power is 1. We know that. This here is saying e to the first is e. Okay, so it's just those same exact properties, just written in ln form. Here, our ln and our e cancel because they are inverses of each other in both logarithmic and exponential form. So here we want to use the graphing calculator to approximate values of log x. Okay, so our parent function here is log base 10 of x. So if we kind of form a table, remember the inverse of this is 10 to the x. So if we form a table with that, okay, let's say -2, -1, 0, 1, and 2. Okay, so maybe it's easy to start with positive ones. So 10 squared is 100. 10 to the first is 10. 10 to the 0 is 1. And then you have 1 over 10 and 1 over 100. When we go to log of x, remember that since those two are inverses, let me just change colors here. Since those two are inverses, the x's and y's switch spots. And we had talked about a quick way of finding these xy ordered pairs. So 1 over 100, 1 over 10, 1, 10, and 100. So then you have -2, -1, 0, 1, and 2. And you can change your axes on how they go. So all I ask is that if you change it, that you kind of start writing numbers. So we have like 10, 20, 30. Okay, you write a scale here if you go by something else. Okay, so we're at -2. Sorry, we are at 1/100th, comma, -2. 1/10th, -1. 0, 1. Get rid of those because I went by ones. And then 10, 1 here. And then the other one's off my graph. So we can kind of just go like this, and it's very sharp, just like that. Okay. Okay, so let's just kind of reiterate a few things that we've been discussing. So domain here, you have a vertical asymptote at 0, so that'd be 0 to infinity. And your range would be all reals. And before we had talked about increasing and decreasing portions of graphs. Know that this graph right here always has a positive slope. So it is always increasing. So on the domain, that is where it's increasing. Okay, so remember, looking for those positive slopes on increasing, looking for the negative slopes on decreasing. Okay, so some word problems here. and that is the perception of the loudness in decibels of a sound with physical intensity I is given by this. Okay, so here's our equation here, where I sub 0 is the physical intensity of a barely audible sound. Find the decibel level of sound whose physical intensity is 100 times that of I sub 0. Okay, so we have this equation here, and we have that it is 100, that I is 100 times I sub 0. So that's what we're going to plug in here. So we have 10 log, and that log has a base 10, 100 I 0 over I 0. Okay, your I sub zeros cancel out. So you have, and we'll come down here, you have 10 log. And if you want to write 10, that's fine. You don't have to. And since these cancel out, we have 100. Well, 100 is 10 squared. Okay. One of our properties here is that the base, see, I have base log 10 and I have an exponential log 10. So these are actually going to cancel each other out and you get 2. So now we have 10 times 2, which is 20. So your label here is 20 decibels. Right here it says find the decibel level. So 20 decibels in that problem. So some of those properties that we've worked with or seen with logarithms can really shorten how you handle logarithms. Okay, evaluate the natural logarithm function. Okay, so here, just using some of those properties, this ln and this e cancel each other out. So you can show that, and then you get 8. I can rewrite this one to be a little bit helpful. If I move this to the top, that's ln e to the negative 2. And again, your ln and your e cancel, so you get minus 2. This one, nothing really cancels out, so we can put that into the calculator. So if you type ln, which is kind of on the left there, and then put 5 in there, enter, that is about 1.6094. And remember, we put the 2 little squiggly lines there to note that we rounded something. Okay, find the domain of the function. Now, we've been talking, or when we graphed the parent functions, you should have noticed that all parent functions, the domain is greater than 0, okay? Which means that this stuff in here, the items inside the logarithm, has to be greater than 0. So 4 minus x squared has to be greater than 0. You cannot have a negative number in the logarithm. For the same reason we talked about exponentials, like if I have 2 to the x, that number is not going to be some negative number. There's no x value for the negative number. And remember, with exponential, our range was greater than 0. So the domain of logarithms has to be greater than 0 because the domain and range switch because they are inverses. So I need to solve this right here. Okay, so when I solve this, I can move this to the other side, or we can kind of say that we can ignore this right now. Remember, this is a parabola. If I rearrange it, it's negative x squared plus 4 greater than 0. If I factor out a negative, I get x squared minus 4 greater than 0, which I can factor that. So x plus 2, x minus 2 greater than 0. So if I have my number line here, I have -2, open circle, and a +2, open circle. This parabola opens down because of this negative. And I want to know, when is my parabola greater than 0? Well, this thing is greater than 0 between these two numbers. And I cannot have them because they were open circles. So parenthesis -2 to 2 parenthesis. So this is my domain, meaning I can choose any number in between -2 and 2 and plug this in and actually get X values. Okay. And we could double check that on the graph, it's only graphing between these two. Draw the graph of the function y equals x ln 4 minus x squared, and use it to find the asymptotes and local minimum and local maximum values. Okay, so remember that the domain, we kind of just found the domain of this portion right here. Okay, this can be anything, but this portion right here had to be between -2 and 2. So to start a graph, we're just going to start a table because I have no idea what this might look like, because it involves a logarithm, a linear, and a quadratic. So that can be really strange. So we're just going to test some values. We're going to make a table of values. Again, I can't have those numbers, so maybe I pick -1.5, and the max I pick is 1.5. Okay, and then maybe -1, 1, and 0. Let's start there. So you can plug this into the graphing calculator to help you get the table. Just be very careful when you go to plug it into the graphing calculator that you get it typed in correctly. Okay, so looking at the table, -1.5 is -0.8. -1 is -1.1. 0 is 0. And 1 is 1.1. And 1.5 is 0.84. This is 4, and this is 0.84. So we have some symmetry here. So if I go to graph this thing, we don't really need a lot here because we can only be between -2 and 2. Okay, so I'm at -1.5, -0.8, so maybe about in there. -1, -1.1, so there. 0, 0. 1, 1.1, about there. 1.5 and 0.84. Okay. Now, I don't really know how to connect this thing. Like, does this keep going down? Does it turn again? So what we can do is we can look at some more numbers. Let's put in -0.5, -0.5, and 0.5. So -0.5 is -0.66, -0.5, -0.66, so about there. So this is kind of turning and going this way. So we had symmetry, so this is going to be 0.66, and you can check that. So about here. So I know that these are going this way, but what happens as I get closer and closer and closer to +2, what happens? So maybe put point or 1.7, 1.8, 1.9, put those in and let's see what happens. So 1.7, you get 0.177, 1.8, you get -0.5, 1.9, -1.78, and you can put 0.99 and see what happens, and you're going to see that I keep getting closer and closer to 2, but I can't actually have 2. So this end comes down like this, and it slowly, as I go down, approaches this positive 2. And this one has symmetry. So as I come down here, it's going to turn and it's going to go up and up and up and slowly approach negative 2. As x goes to negative 2, y goes to infinity. And that's some of those end behaviors that we have talked about. So we actually have vertical asymptotes at x equals plus minus 2. Okay. And we have local maximum and local minimums at this point right here and this point right here. Now, we would actually need to find those on the graph. We may say that, oh, it might be at -1, -1.1. But if we look on the graph, we've talked about actually calculating a minimum or calculating a maximum. And if we do that, let me just see if I can show you here on the calculator. Okay, so okay, so this is what our graph looks like. You can see it only goes between -2 and 2. It actually goes on forever, like down, but our calculator can't really see that. So if I want to find this maximum, local maximum here, so that second calculate maximum, we're going to go to the left of it, hit enter. We're going to go over to the right of it, hit enter. And you can see it puts those two vertical lines sandwiching. Then it says guess, so you can come over here and be like, I think it's right there, hit enter. And it tells you that the maximum is at x being 1.15, and then the y is 1.13, which we plugged in 1.5 and 1, but this is in between. So it's kind of hard to see unless you choose every single value. So going back here, so our local max here, so this was 1.15 comma 1.13. And then to find the minimum, we're going to hit second calculate minimum. Whoop, that was maximum. So 3, and I'm going to scroll over to the left of my minimum, enter, scroll over to the right of my minimum, enter, sandwiches, guess, come over here, enter, and then it says -1.149, -1.132. Again, we have that symmetry here. So this is -1.15 comma -1.13. So have symmetry about the origin there, which we've talked about odd even functions, and this applies. Okay, so that's part 2 of your 4.3. So you have your web assignment that you can be working through. If you got questions, feel free to let me know.